So in section 4.7 we're going to be talking about a specific kind of pattern that we see in our functions, which is called arithmetic sequences. So we're going to be doing things like identifying and extending patterns that we find and also representing arithmetic sequences using some specific functions in function notation. So the first question there is kind of an example that you can look through to get the idea of what arithmetic sequences are using. But eventually, if I solve a question like the one that was given, the numbers of pieces of wood used for one section of fence, two sections of fences, and so on form a pattern or a sequence. So if I keep adding fences to that, I could see that there's some sort of pattern that happens with our pieces of wood. So a sequence is an ordered list of numbers that often form a pattern, and each number in the list is going to be a term of that sequence. So every number that's a part of that sequence is a term. When you can identify a pattern in a sequence, we can use it to extend the sequence. That means just to get a few more numbers at the end of your pattern. We can also model some sequences with a function that we can use to find any term of the sequence. And that's going to be important when we're making those later. But first, if we're just going to describe the pattern that's happening in each sequence, we can also then just use that pattern to find the next two terms of the sequence. And in that first practice problem, if we're going to try that, it looks like to go from one number to the next, I have to just add 6 to the previous term. So 5 plus 6 is 11, plus 6 is 17, plus 6 more is 23. So if I extend that to find the next two terms, if I add 6 to 23, I get 29. Add 6 more, I get 35. So those are my next two terms. Same idea with the others. If I take this pattern, it looks like every time I divide the previous term by 2. So in that case, if I kept going, I divide again, I get 25, and one more is 12.5 or 12.5. Next pattern that I see, if I have 2, -4, 8, and -16, looks like every time there, I have to multiply my previous term not by a positive, but by -2, because I switch signs every time. So if I keep multiplying by -2, -16 times -2 is 32, times -2 again, I get -64. Last pattern, if I have -15, -11, -7, and -3, looks like every time here I'm adding 4 to the previous term. So if I kept adding 4, I would get 1 and 5. So these kinds of questions, we just have to describe the pattern and then use that pattern to get a couple more terms. Also an arithmetic sequence, so our specific title of the sequence that we have, the difference between consecutive terms is constant. This difference is called our common difference. So we actually saw a couple arithmetic sequences here. When I was finding the difference between those, I always added 6, always added 4. Things like multiplying or dividing those are not going to be examples of arithmetic sequences. But more specifically, if I want to tell whether it's arithmetic, again, if I have a few more patterns, I can also tell the common difference if if it is an arithmetic, I should have a common difference. So in the first sequence, it looks like I add 7 to get from 8 to 15. Add 7 more, I get 22. But then if I add 8 more, I would get 30. So since this is not always the same difference between your two numbers, first I have 7, then it changes to 8, that would not be an arithmetic sequence. Next example, if I have 7 and I add 2, that would give me 9. Add 2 more, I get 11. 2 more is 13. So this is an arithmetic sequence. So yes, I can tell it's arithmetic. And your common difference there is 2, because the difference between all of those terms in the pattern is just plus 2. My next sequence, I have 10, 4, -2, -8. So since every time there it looks like I'm going down by 6, subtracting 6, first of all, that is an arithmetic sequence. I can tell that my common difference is a -6, because I'm always going down with that value by 6. And our last pattern, I have 2, -2, +2, -2. So you could always interpret this as being multiplied by like a -1 every time. But if I want to find a common difference, I subtract 4, then I add 4, then I subtract 4, and I add 4. So if I keep going back between those two, that's not going to be arithmetic, because it's not consistently always adding 4 or always subtracting 4. Our sequence is a function whose domain is the natural numbers. So again, domain, you want to think your inputs or your x's. And by natural numbers, we mean, again, like counting numbers. Start counting with 1, 2, 3, 4, so on and so forth, and whose outputs are the terms of the sequence. So we can write a sequence using what we call recursive formula. Recursive formula is a function rule that relates each term of a sequence after the first to ones that come before it. And it is important that we need the first term, so we need a starting point, but everything that comes afterwards I can write with recursive. So if I consider this sequence, 7, 11, 15, 19, we can use the common difference of the terms of that arithmetic sequence to write a recursive formula for the sequence, And for that sequence, the common difference was 4. To go from one number to the next always looks like I am adding 4. So if I want to make a recursive formula, we're going to define a few things first. So n is going to be the term number of your sequence. So if you're on term 1, that's your first number, term 2, term 3, so on. A of n is going to be the value of that nth term of the sequence. So again, if this is written in function notation, this would be your output after I input my term number. So if I was looking in that pattern that they give us up above, first term is 7, and if I want to get term 2, I can take the first term, so the one that came before it, and add 4, so I get 11. So then if I want term 3, that's a of 3, that means I need to take the term that came before it and add 4. So if I do 11 plus 4, I get 15. Same thing for the next one. If I have term 4, that's taking the term 3 and adding 4, so I get 19. And if we're filling in our own step, again, we have to write in that to get the value of term 5, that's a of 5, I find that by taking the previous term, and that was your fourth term, a of 4, and I add 4 to that value. So 19 plus 4 gives us 23. So if I generalize that, it looks like if I'm doing 1, 2, 3, 4, 5, and so on, I can just say I can use any number n. And again, if I always use the term that came before it for that value, I can just say that's going to be n minus 1. So that's just 1 before your term that you're currently on. And then we just add 4, and that's always your pattern. So the recursive formula for that arithmetic sequence above is basically that last line, a of n equals a of n minus 1 plus 4. So I take my, to find my term, I get the term that came before it and add 4. And we also need for all our recursive formulas, we need a starting point. So it also says that your first term, a of 1, is 7. So if I'm using that same pattern to write a recursive formula for each sequence that I have that's arithmetic, what that's going to look like in this first example is if you're always adding 6, so plus 6 plus 6 plus 6 gives me my next number. First thing I need to do is make sure I know what the first term is. You always need a starting point. If I don't have a starting point, we don't know what to add. So the first term I want to make a note is 3. So a of 1 equals 3. You need that as part of your formula. And for the formula itself, this first part is never going to change. I'm always going to have a of n equals a of n minus 1. So that's saying your term value is equal to the one that came before it. But this part, I need to make a note of what I'm doing in my pattern. We're always adding 6, so I take that previous value and add 6. And it's also asking me what's the 9th term. So there's not really a better way for recursive other than keep your pattern going. So 5th term is 27, 6th, 7th, 8th, and 9th term would make 51. Same thing for part B. Again, we always have to list a starting point, so it looks like I start my pattern at 23. And if I have a recursive formula, that means a of n is going to be equal to a of n minus 1 plus or minus something. So I start with that previous term. And then this example, it looks like I'm adding 12 every time. So I take that and I do plus 12. So again, first part is always going to be the same, that a of n equals a of n minus 1. It's only when I get to my common difference at the end that's going to change. And also if I need the 9th term, I keep extending that pattern until I get to, looks like 119. For part C, same idea. So want to make sure you have your first term listed, that's 7.3. Then that recursive beginning, a of n equals a of n minus 1. And this time it always looks like we're adding a half, so you can do plus 0.5. And if I keep my pattern extended for 9 terms, it looks like that's 11.3. Last example, again we need a first term, so first term is 97. We also have that recursive start, so a of n equals the previous term. And this time it looks like I always subtract 9, so minus 9. And again, if I keep that pattern going for 9 terms, I should eventually get to 25. So we're also asked, is the recursive formula a useful way to find the value of an arithmetic sequence? And I would say it kind of depends. My example, it's only really useful for finding values of terms that are close to ones that you already know. So if I'm looking for the 9th term, that's close enough to the ones that are already listed. But say, for example, if it asked you for the 100th term or 1000th term of the sequence, that'd be kind of hard because you'd have to keep going in that pattern 100 or 1000 times. So we actually have a better way of doing that on the last page, which means we can find the value of any term in an arithmetic sequence using a recursive formula. We saw that before. But we can also write what we call an explicit formula. An explicit formula is a function or rule that relates each term of a sequence to its term number. So the nice thing about this is I can go right into my sequence and get my value right away without looking at any other terms. So that explicit formula is always going to be the same kind of form. The nth term of an arithmetic sequence with, again, a given first term, a of 1, and a common difference of d, we always use this sort of formula for explicit. So again, a of n is your nth term, whatever term you want to find. A of 1 is whatever term comes first. Then I'm going to do plus, and in parentheses, n minus 1, because again, that's looking at your term number, and then take away 1. And then if I have times d at the end, that's timesing by your common difference. So whatever your common difference is, we're going to multiply that at the end, and notice that would eventually be distributed if you're using that rule. So looking at that kind of example in our first practice question, Subway Pass has a starting value of 100. So again, if I see starting value of 100, starting point might be important. After one ride, the value of the pass is 98.25. After 2, it's 96.50. After 3, it's 94.75. So we're going to use that to write an explicit formula to represent the remaining value on that card as an arithmetic sequence. And we also want to find the value after we reach 15 rides. So first thing I did was I listed just the general form for your explicit formula. Again, that's the same thing we had up here in the definition. A of n equals a of 1 plus the quantity n minus 1 times your common difference. And remember, in order to start this, I really just need two things. I need a starting value, and I need to know what the common difference is. So your starting value, it told us up here that it was 100, so I already know that when I plug a of 1 into my function, I'm going to have 100 for this piece. And I also know my common difference because every time I use that pass, it looks like we're taking away $1.75. So my common difference is minus 1.75. So in that formula, what we're going to have is, again, 100 is your starting value. So we have your a of 1 starts with 100, then your n minus 1. That part's not going to change. And we just want to make sure we include that your common difference multiplied towards the end is a minus 1.75. And we're just plugging those parts in your explicit formula, and that's the only two parts you need, is the starting point and that common difference. So if I want to find out the value of that pass after 15 rides, this is a little tricky based on how we wrote our formula. We actually have to look for the 16th term, because remember, technically the first term was before we even wrote it, so that's after 0 rides. So if I want to find after 15 rides, I need to plug in the 16th term, so 0 rides going up to 16. And if I plug 16 into my function, I should get 73.75. We can also answer the question, how many rides can be taken total with your $100 pass? I can find that out by setting that value equal to 0. So again, basically we want to see how long would it take for that value in the card to go down to 0. So I can just use that formula. So 0 equals my explicit formula, starting value plus n minus 1 times your common difference. And I just work through my steps by distributing. So multiply both of these by the negative 1.75. I subtracted 100 and subtracted 1.75 over to the left-hand side. And then if I divide by negative 1.75, I get about 58.1. But remember, what this means is that we actually have to start by taking away 1, just like in that last example, because our starting point was before we had any rides. So if I take away 1 from that ride total, I get 57. And again, I can't round up because I don't have enough money for that extra ride. So we can also write an explicit formula from a recursive and vice versa, so we should be able to change between the two. So these last two practice questions, it looks like we start off with a recursive formula that's given. So again, I see a of n equals a of n minus 1. So that's your recursive start, and then I do plus 2. Remember, every time we see recursive, it should have a starting point. So if I just take those two parts that I need for the explicit, two parts that I need are my common difference. So my common difference is plus 2, and my first term is 21. So as long as I'm using those in the explicit formula, kind of like what we saw earlier, I plug in my starting point and then n minus 1 times your common difference. And I'll just kind of show my answers to the last few because those work about the same. Again, as long as I'm plugging in my common difference and my starting point, I should be able to go from recursive to explicit. And if I want to go vice versa, again, I still have a starting point in explicit. So 76 is my first term, and 10 in explicit just comes at the end, so that's my common difference of plus 10. So same thing if I start with 1, and then my common difference is 3. We just have to make sure we can write that in either form. So make sure we come in with questions on anything we didn't understand, and that way we can work on the practice in class.